Okay. Good morning, everyone. Welcome to my thesis defense presentation. The title of my thesis is Structural and Climatic Effects of Large-Scale Basaltic Magmatism, Constraints and Insights from Geodynamic Models. As you know, my advisor is Roger. The Earth's history has shown us plenty of evidence for supporting this sentence by Will Durant. And massive magmatism in place globally throughout the Earth's history could cause existential crisis for any living beings on Earth. In general, this work is about three effects of massive magmatism: the assisting of breakup of continents, controlling the up and down topography of volcanic plateaus, and causing global warming by releasing significant amount of CO2 into the atmosphere. And specifically, I attempt to address three major questions by modeling the emplacement of magmatism. The first question is, what was the plate strength during the rifting of continents? The second question is, what causes the completely opposite topography of the two most recent volcanic plateaus, the Ethiopian Up Plateau and the Columbia Down Plateau? And the third question is, why global warming could happen 100,000 years prior to the main phase of flood basalt volcanism. Here is an outline of the three chapters of the thesis. And the first two chapters focus on the tectonic effects of the continental large-scale basaltic magmatism. Built upon the insights from the first two chapters, the last chapter looks at the timing of flood basalt volcanism relative to global warming. So the first question, what was the plate strength during rifting? We know that massive volcanism happened throughout the Earth's history and formed the Large Igneous Provinces, mostly along plate boundaries, assisting the breakup of continents. For example, the Central Atlantic Magmatic Province, or CAMP, happened at the Triassic-Jurassic boundary about 200 million years ago, contributed to the breakup of supercontinent Pangaea and the formation of Central Atlantic Ocean. As we all know, the foundation of building at Lamont, the Palisades Seal, are part of CAMP. During the volcanic rifting process, an upwelling mantle plume impinges at the bottom of the plate, bringing in great amount of heat that generates voluminous melt that can erupt to the surface, like this magma fountain up to tens of meters high erupted in 2014 on Iceland. So to address the question, what was the plate strength to allow continent to rift apart? We look at the seaward-dipping reflectors at volcanic rifting margins. They deposited globally and indicated by these red curves. So what are SDRs? Let's take South Atlantic as an example. Here's a cartoon showing a rifting margin, and SDR are deposited and seismically imaged massive lava flows deposited near the continent-ocean transition zone. And zooming in, we can see oceanic crust on the left, continental crust on the right, and these seismically imaged reflectors that dip toward the ocean. That's where the name seaward dipping comes from. In the next few slides, I will show how do SDRs provide unprecedented information to look into the historical plate strength. Here's a depth-converted multi-channel seismic profile offshore Argentina, South Atlantic. At the continent-ocean transition zone, we see these reflectors that dip toward the ocean, sitting beneath 4 kilometers of post-rift sediments. They usually have a concave upward shape, and each wedge thickened at depth. The SDR wedges generally has a spatial domain of tens of kilometers across, up to thousands of kilometers along strike, and several kilometers thick, resulting in a total volume up to 1 million cubic kilometers, similar to that to LIPs. And so how are SDR formed? Well, drilling offshore Norway indicate there are thin layers of sediment interbedded within thick piles of lava. Bowerson and Walker first proposed crustal drift and lava loading for producing the 2D lava flows on Iceland. Here's the rifting center, and AA prime shows these 2D lava flows dipping toward the rifting center. But how do we relate the plate strength to these bending lava flows? The research approach is that because the plate strength controls the SDR geometry, and so the geometry can reduce the plate strength. And basically, based on thin elastic plate theory, with the same loads on the left, the weak plate with low elastic thickness will have more bending, whereas strong plate with high elastic thickness will have less bending. And Roger develops the crustal drift and dike loads idea and first quantitatively describe the physical relationship between magmatic loads, plate strength, and SDR geometry. When a fluid dike open at the rifting center, we assume it has a density around 2800, similar to that of lithosphere or similar to the country rock. And as it solidifies, it will load the plate downwards and cause the bending. Magma lava flows further loads the surface downwards. And repetitively, as the old dikes move off axis, new dikes keeps loading the surface downwards. It can cause these bent lava flows that looks like the observation. In order to tell the plate strength, we need observables to link SDR geometry to that. And based on the math derivation, identify 3 observables of SDRs. The first observable is XF, which is the horizontal distance between the most bent reflector and the tip of the flat reflector. It's proportional to TE to the power of 3/4. T is the elastic thickness. And the second observable is gamma, which is the ratio between the total thickness of SDR and the tangent of the deep angle at this point, which is also proportional to the power of 3/4. When this part of the data is not available, we need a third observable, which is phi. As you can see, phi is almost constant along all the reflector tip, which is the angle between reflector tips and the bottom boundary of SDRs. So when this part is not observed, we can measure phi from here, and it's proportional, the tangent phi is proportional to TE to the power of minus 3/4. Using the 3 observable, we can estimate an average elastic thickness TE of 2 kilometers from this profile. And we can then use this as an input parameter to generate a elastic model profile that looked like the data. So the analytic plate model can reproduce general features of SDRs and explain their formation, but has several assumptions like elastic thin plate. And this assumption could introduce inaccuracy. The major one is this elastic thin assumption. So the yield strength envelope for this case looks like this, and you have the maximum extensional and compressional stress at the surface and at the bottom. However, for more realistic elastoviscoplastic EVP and thick plates, the yield strength envelope look like to the right. And when you overlap the two, you can see the difference. The red parts indicate the missing strength due to brittle deformation, and the blue part indicate missing strength due to ductile flow. So overall, the bending moment a thick EVP plate can sustain would be much smaller than analytic thin elastic plate. In order to map lithospheric thickness H of L to effective elastic thickness TE, we need to quantify effects of different assumptions for between numerical lithospheric thickness H of L and analytic elastic thickness TE on plate strength and SDR geometry. To do that, we built a series numerical thick plate model with different rheology. And to say for the interest of time, I will only present one example from the M3 model with thermal evolution and density structures. So as you can see, here's the model setup. We stretch on the right with a constant rifting velocity 1 centimeter per year. And initially, upper crusts are flat, and we intrude dikes into the rifting center that has a higher density that will load the surface downward and cause bending. And we fill in lava loads on top whenever the surface bends down. The numerical lithospheric thickness H of L is quantified from the surface to where differential stress is less than 5 MPa. Let's take a look at one of the model run. Initially, the upper crust is flat, and then as the denser dike load the surface down, we fill in lava, and as you can see, the flat surface is bent now. Due to the bending stress near the surface, it caused brittle deformation indicated by this plastic strain. And the bending also caused compressional stress indicated by this blue color. Because of the heat input from the dike, the rifting center has the thinnest lithosphere. And here's the viscosity structure. Eventually, it formed these bent lava flows that tilted toward the rifting center. Looks like the data. And here's the results. So we have a lithospheric thickness for this model, 16 kilometer. And we measure the observable and can estimate the TE from this geometry. And we also run another 15 models with different H of L. Here is the model result summary. If it is elastic thin plate, it should be 1-to-1 relationship between TE, analytic elastic TE, and the numerical lithospheric thickness. However, due to brittle deformation, the elastic plastic thick plate model show a decrease in strength. And due to missing of ductile flow, the EVP thick plate is the weakest. We use the most sophisticated EVP thermal model to map the data onto our numerical mapping. And the Vorin margin and Argentina margin show a TE from 1 to 3 kilometers that map to lithospheric thickness from about 3 to 6 kilometers. So to address the first question, we have our conclusion here. We derive 3 observables, and then that help us to estimate the elastic thickness of SDRs from 1 to 3 kilometers for the 2 margin. And then we develop a 2D thermo-mechanical model to map the TE to lithospheric thickness H of L to 3 to 6 kilometers. Mental potential temperature might be a major control. Now let's move on to second question. What control the up versus down of volcanic plateaus? And we first take a look at the data. So we know Ethiopian Plateau comprised of Ethiopian flood basalt erupted during Oligocene, and Columbia Plateau are formed with Columbia River Basalt erupted during mid-Miocene. Both are the most 2 recent large igneous province, but show opposite topographies indicated here. Ethiopian is about, the center is about on average 1.5 kilometer above the surrounding, whereas Columbia Plateau is on average 0.7 kilometer below the surroundings. We know that based on seismic and petrologic data, the intrusive volume is a lot more than the extrusive volume. So that this suggests crustal intrusion could be very important for the buildup of volcanic plateau topography. The surface heat flux is much higher for Columbia River Basalt than that of the Ethiopian Plateau. And this indicate much hotter crust beneath Columbia Plateau. And so this also suggests crustal thermal structure could be also very important for the buildup of plateau topography. Based on this information, we have our conceptual model for high plateau with cold and strong lower crust with massive intrusion. Because of the high pressure due to intrusion at the center point here, the crust will try to flow laterally. However, because the thicker lithosphere and strong lower crust block the lateral flow, the high plateau can persist. However, when the crust is hot in the lower crust with low viscosity, then pressure gradient will drive lower crustal flow easily, and eventually the intrusion into the lower crust will be distributed evenly, and the mechanically attached upper crustal dense intrusion will be able to pull down the surface and form a low plateau. And then we build a simple semi-analytic model assuming thin channel for lower crustal flow. We assume linear temperature increase from the surface to the mole temperature T of M, and then that gives rise to the log scale viscosity structure increasing to the surface. And the main thing we model is crustal thickness, H of X, and it is governed by this diffusion equation. The diffusivity, kappa F, controls how fast the lower crustal flow can be. And kappa F is a function of Y0 and eta 0. Eta 0 is the viscosity at the mole, and Y0 is a vertical length scale for the thickness of the fastest part of the channel flow. As you can see, kappa F, both Y0 and eta 0 is a function of temperature at the mole. So we are going to focus on changing temperature at the mole for its effect on the topography offset delta W. And here is the our model summary. When we increase our lower the mole temperature to the right, a high plateau is formed, whereas hotter mole temperature will cause a low plateau. And different color lines just for different model setup for CP, Columbia Plateau system or Ethiopia Plateau system. And we then use another parameter, characteristic time for lower crustal flow, tau LC, which is the ratio between the total area, the width of the seal, times the total thickness of the seal over the diffusivity. Basically, the longer the tau LC means the slower the flow or the smaller the diffusivity. And same thing happens, as you can see, longer crustal characteristic, lower crustal flow tau LC create a high plateau, and faster tau LC produce a low plateau. And this model results suggest 10 to the 14 seconds of tau LC is the boundary value for separating high versus low plateau. Based on this information, we then build a numerical 2D thermo-mechanical model, elastoviscoplastic with EVP rheology. And again, we vary the initial thermal structure to see its effects on plateau topography. The model setup is similar to that of the seaward-dipping reflector model. It's just that we don't stretch on the right, and the dike intrusion has been replaced by seal intrusion indicated here. Here's all the model results summary. As you can see, the high plateau is on the right with longer characteristic timescale for lower crustal flow, whereas the low plateau is on the left with smaller or faster lower crustal flow. And again, we found that the boundary for separating high versus low plateau is about 10 to the 14 seconds. Let's take a look at one example of high plateau with tau LC 4 times 10 to the 15 second that result in a 1.2 kilometer of delta W topography offset. As you can see, here's the final topography, a high plateau. And here, oh, by the way, this is with normal thermal gradient, 30 Kelvin per kilometer at the surface. And here's the model result. As you can see, there is high viscosity in the lower crust. So as the seal intrudes, it will cause the thickening of the crust. And because of the high viscosity, the resistance tracks block the lateral flow in the lower crust. So the thickening of the crust causes a persistent uplift of the surface, creating a high plateau. And there's warm-up crust due to the intrusion. Now let's take a look at a case for a low plateau with less than 10 to the 14 second tau LC, which result in minus 600 meters of plateau topography shown here. It has a higher thermal gradient of 40 Kelvin per kilometer. And here's the model run. Now it's much hotter in the lower crust and with much lower viscosity. As the seal intrudes, it's able to generate pressure gradient and drive lower crustal flow much faster. Initially, there's some uplift, but because of the fast lower crustal flow accommodate the intrusion space, and also because the intruding material densify as it solidify, it's able to pull down the surface and create a low plateau eventually. So to address the second question, what control the up-down topography of volcanic plateaus, we focus on the crustal intrusion effects. And we first built a simple semi-analytic model to see the effects of lower crustal flow on a wide range of rheology and geotherms. And then following that, we built a 2D numerical thermo-mechanical model. And we found that to generate a low plateau, it not only requires very fast lower crustal flow, but also a significant amount of intrusion densify and is able to mechanically attach the strong upper crust to pull down the surface. For a slow lower crustal flow or characteristic time scale larger than 2 times 10 to the 15 seconds, a long-lived high plateau result no matter the style of intrusion. Synchronous substance of flood basalt extrusion is also modeled from our results. And if assuming the main phase of flood basalt eruption occurs only when the average density of the crust above the seal exceeds the density of the fluid magma, which I will talk in more detail in the next chapter. So to address the third question, what caused the global warming 100,000 years prior to the main phase of flood basalt volcanism? Let's look at our chapter 3. Flood basalts are the surface extent of large igneous provinces. They are the Earth's largest volcanic eruption episodes when significant portion of biological species went extinct. And they also correlate in time with hyperthermal events. For example, the largest Siberian trap correlate with Permian and Triassic mass extinction and the hyperthermal. The Deccan Traps correlate with the Cretaceous Paleogene mass extinction, the most famous extinction of dinosaur. And also, as I will show, there's a big warming events around that boundary. Today, we are going to focus on the Deccan Trap and the Columbia River Basalt for this chapter. The Deccan Trap are basaltic lava flows that cover about 20% aerial extent of India and has an average thickness of 2 kilometers. What triggered this more than 1 million cubic kilometer of lava extruded onto the Earth's surface is still controversial. However, recent geochronology and climate data might shed light on this process. So panel A shows the elevation map of Western Ghats, India. The black line denotes cross-section XX prime shown at the bottom. Geochronology samples are collected at where indicated with the color dots. The volumetric stratigraphy column on the upper left is estimated with geochronology results for timing of eruption and with the thickness of each formation. Converted that with time, you can see this graph showing time from left to right. And here's the extrusive flux indicated by this color box, where what you can see is that onset of more than 75% of total volume of Deccan Trap was erupted after the Cretaceous Paleogene boundary. And a recent paper compiled benthic del 18 data globally, was able to find a global temperature change at around that time. And they found a 2 degrees C warming 100,000 years prior to KPG. When we overlap the two data together, we can see the onset of global warming was 300,000 years prior to the onset of major phase of flood basalt eruptions. Now let's take a look at Columbia River Basalt that was erupted around Miocene. Similar trend happens. So as you can see, this is the del 18 data, and another study using geochronology dating of the flood basalt indicate 95% of total volume was erupted 400,000 years after the onset of warming. So from these two intriguing data, we try to ask a question: what caused the abrupt global warming 100,000 years before the flood basalt main phase of flood basalt volcanism? To answer the unknown, let's first take a look at some observational constraints. So first of all, we know that the intrusion beneath these LIPs has much larger volume than that of extrusives. And seismic velocity and gravity anomaly beneath Deccan Trap indicate higher velocity structure, and also higher gravity anomaly indicate denser crust beneath this flood basalt. Same thing happens for Columbia River Basalt, higher gravity anomaly and higher seismic velocity. With our chapter 2, which indicate you need denser crustal intrusion to pull down the surface, that also indicate denser crust. Then we look at the relationship between magma and CO2. We know that CO2 is very sensitive to the pressure in the magma. When the magma ascends with lower pressure, CO2 should exhaust almost completely. And also it has very low partition coefficient in the magma. So when magma crystallizes at depth, CO2 could exhaust from that. Field evidence from Yellowstone or East Africa rift indicate very high CO2 flux from the surface. So to summarize, CO2 could exhaust from crystallizing low viscosity basaltic magma and go up quickly under buoyancy through cracks or the transcrustal magmatic systems. Now, to address the initial question with all the observational constraints, we can translate that question into a new question. Is it possible to have larger volume of magma intrusion that release CO2 to the atmosphere and cause warming some 100,000 years prior to major phase of eruption? And to answer that question, we need to first answer what controls timing of main phase of flood basalt eruptions. And we propose crustal density filter for controlling large-scale magma eruption. The physics is very simple, just water level device. If both sides has the same density, say crustal density, and the pressure is the same at bottom, then they should reach the same level. However, for a little bit denser magma, given the pressure provided on the left, the magma won't reach the surface because it's denser. But if you replace significant amount of the crust with solidified denser intrusion, then the pressure is higher. So it's able to allow the magma to reach beyond the initial surface. And there's evidence from mid-ocean ridge basalts shows that the eruptive mid-ocean ridge basalt lies within this window of eruptibility, where their iron content allows them to have a more buoyant density than the crustal density. Also, a deeper magma length correspond to thicker extrusive, showing the similar physics. So if we have low density country rock, then that of the magma density, then the magma cannot erupt. However, if we have denser country rock and has a higher density overburden, it will drive the magma to erupt. We know that the density increases with depth for the Earth. So let me illustrate with a simple two-layer density structure and show the importance of depth of sill. If we have a shallow sill, then the overburden density of that sill is less dense than the magma density, so no eruption. However, if the sill is able to is at a deeper depth, the average density of the overburden is the average of the blue and the black crust. So the average density could be larger than that of the magma and can drive eruption. With a global average continental crust density and assume a magma density of 2800, you will need to have a sill deeper than 27 kilometers in order to allow it to extrude to the surface. And if sill shallower than that, will have difficulty to reach the surface due to the pressure. However, if we have densified crust for some LIPs, the lithostatic pressure will become higher, and hence a shallower sill is able to extrude to the surface, to supply magma to extrude to the surface. Based on this information, we find the key for determining large-scale eruptibility is to compare the average overburden density of the sill, rho OB, with the magma density, rho M. And when the rho OB is less dense than that of the magma, the overburden form a low density barrier and intrusion is favored. However, when rho OB is larger than that of the fluid magma, then it will form a high density driver to prefer eruption. We assume a constant magma density for the basaltic magma, and then let's take a look what controls the average density for the sill overburden. As we shown earlier, the depth is important. The deeper the sill, the higher the sill overburden. Another thing is important is the density structure. If part of the crust is replaced by densified sill intrusion, then the overburden density for the same level of sill intrusion could become larger and drive eruptions. Now, let's take a look at a conceptual model with 4 stages evolution. Assuming a Gaussian shape of magma supply flux, initially it's low, so the sill can only intrude into warmer and weaker lower crust. And at this point, the upper part overburden density is less dense than that of magma, and it's mostly intrusion. As the magma flux increases, the sill is able to intrude to shallower depth. And again, the overburden density is less dense than that of magma. And then as we keep increasing, the flux allow the sill to intrude to the shallowest depth. However, at this point, the flux begin to decrease and the heat input lower. So the sill is not able to sustain the heat loss to the surface at that shallow depth. The sill has to intrude into much deeper depth. But because this part of the upper crust has been replaced by the previously intruded sills, the density structure along with the deeper sill depth cause the average density of the sill overburden become larger than that of the fluid magma, and main phase eruption happens. Then based on this idea, we build this analytic steady state model for relating the flux F of M to intrusion depth of the sill, assuming again a Gaussian shape of flux of magma. The heat input scales with intrusion flux. So the heat input Q in is scales with F of M. The heat lost is just scales with the thermal gradient. So it's the temperature of the magma divided by the depth of the seal, Z in, and times the heat conductivity. When we equate the two, so the heat is balanced, then we can find that the seal intrusion depth is inversely proportional to the magma flux F of M. Here is a plot of that. So here's the flux, and here is the seal intrusion depth. Because of the seal first intrude upward and downward, replace the part of the crust with densified seal. As we go back down, the average overburden of the crust become denser than that of fluid magma. And here is the point where onset of main eruption phase could happen. And as you can see, it's after the major intrusion happened. And this model has several limitations because of simple assumption like instant heat transfer. It causes error in timing. So built upon Annan 2006 numerical multi-seal model, where a series of seal intruding into the crust and to perturb the thermal structure. And also we consider there's no density and mechanical consideration for seal depth, but we are going to explicitly determine seal depth based on the crustal thermo-mechanical condition shown here. So basically, every time the seal intrude at a depth with maximum breakout pressure, which I will describe now. So we would let us zoom in this part. Because the crustal density increases with depth, lithostatic pressure, PL, show increasing gradient with depth. Assuming constant magma density, a magma reservoir at the borehole and magma within the reservoir has the same pressure as the lithostatic pressure. We have the magma static pressure shown with the red dashed line. Along an open conduit from the reservoir up, due to density difference between the magma and the crust, magma overpressure is computed by subtracting lithostatic pressure PL from the magma static pressure PM, and its maximum at the level of neutral buoyancy, where crustal density equals to the magma density. Physically, magma overpressure means the extra magma pressure compared with the lithostatic pressure, the fluid magma acting on the wall rock of the conduit. And then the green region indicate the resistant pressure for opening a large seal. It comprises the thermal arrest pressure, PTA, and horizontal compressive stress, sigma H. The thermal arrest pressure is the minimum pressure required to drive a fluid magma to intrude in a large distance into the colder country rock before the magma freezes. The horizontal compressive stress, sigma H, is induced by magma overpressure and can be relaxed based on viscosity structure with depth. If near the surface where viscosity is high, compressive stress sigma H is not relaxed quickly, it will prevent further upward migration of magma. You can think of resistant pressure as likelihood for a seal formation. The larger the PR, the less the likelihood. So when you use PD minus PR, we can have a breakout pressure, PBK. And then we find for each time step, the maximum depth for PBK to intrude a seal, which brings in heat and basaltic magma that can later solidify, become denser and stronger. Here is the model results. Again, 4 stages. As the flux increases and then decreases, it forms this seal depth from deeper to shallow and then go back down deeper. We assume a piecewise linear temperature structure here. And here's the solidus, liquidus determining the density of the basaltic intrusion. And the vertical green line is the overburden density, average overburden density, and the red is the fluid magma density. As the flux increases, the seal is able to intrude upwards and warm up the crust and leave behind it a series of solidified seal that densify the crust. As the flux keep increasing, the seal depth go to the shallowest depth. And at this point, what's above is still normal crust, which has an average overburden density less dense than that of the fluid magma, so no eruption happened. Eventually, as the magma flux decrease, the heat input is not able to sustain shallow intrusion. Now the sill jump back down to where it's hot and weak. And at this point, the upper part of the crust has been replaced by densified sill intrusion, and the overburden density now is larger than that of the fluid magma. Whenever magma can come into this sill, the magma can erupt easily to form flood basalt eruptions. As you can see, as the sill crystallize, bubbles of like volatiles like CO2 can escape and release into the atmosphere during intrusion phase. Here is a video showing the process. So the upper part is the sill depth overlap with the flux, and left is the temperature structure evolution, right is the pressure evolution. The main thing to determine eruption is this pressure from the sill. If it is positive at the surface, then eruption could happen. It's equivalent to overburden density compared to that of the fluid magma. So as you can see, as it proceeds with increased magma flux, the sill depth to increase go shallower, and then it go back deeper. And because of the densified intrusion, the magma driving pressure is become larger. And eventually, as the sill depth go back deeper, the eruption could happen. Let's take a look at it again. So now it's mainly crustal sill intrusions. And as the sill go back deeper, the replaced densified crust allowed overburden density to be larger, and then eruption could happen. And then let's take a look at a comparison between numerical model density with that of the observed density structure. So initially, we assume a global average linear density structure. As the sill keep intruding upwards, it replaced the solidified sill become denser and create this densified density structure beneath it. And as the flux begin to decrease, the sill cannot sustain shallow depth, so it begin to go back deeper. At this time, the overburden density is still lower than that of fluid magma, so no major phase of eruption could happen. And eventually, as the sill keep going deeper, the overburden density is now larger than that of fluid magma, and main phase of flood basalt eruption could happen. And we have a density profile to compare with the Deccan Trap, what's under Deccan Trap. We know from samples of like picrites, melt inclusion of picrites, we can know the concentration of barium, niobium, and the ratio between barium, niobium to CO2. These allow us to estimate a range of CO2 concentration of 0.1 to 2% weight percent in original mantle derived magma. And for simplicity, we just assume around 1 weight percent of that concentration. So from the modeled intrusion and eruption volume of magma flux with a assumed concentration of CO2 in the mantle melt, and also with some previous referenced outgassing efficiency from intrusion and extrusion, we can calculate a magmatic carbon outgas flux based on that model results. And this carbon flux can, and here shows the carbon flux based on the model runs. So here's the magmatic flux, and here's the outgas flux with the extrusive flux. When we input this carbon outgas flux into a simple box long-term carbon cycle model LOSCAR, we can then have a atmospheric concentration of PCO2 with time, which lag behind the assumed magma, Gaussian-shaped magma flux. And this CO2 concentration, atmospheric CO2 concentration can be translated to global temperature change to compare with the data. And as you can see here, there's a warming 100,000 years prior to the major phase of eruption. So to answer the third question, what caused the global warming prior to main phase of flood basalt volcanism? Here is our conclusion. We argue that major eruptions of continental flood basalt may require densification of the crust by intrusion of larger volumes of magma that are extruded. And simple model could show that magma crystallization and release of CO2 from such intrusion could produce global warming before the main phase of flood basalt eruptions on the observed timescale. And our model further suggests that the evolving crustal density may have a first order control on timing of the major phase of continental flood basalt volcanism. And that's all of the presentation. Please allow me to share my gratitude. So to Roger, I have several photos taken with Roger, but I chose this one as a good representation of my 5 years interaction with Roger. So this is back in 2016 when I just came out of hospital. Roger was helping me move. And this assembled bunk bed represents the beaten slowness of me, and the powerful SUV represents the persistent drive from Roger. It has been a long and tough journey for me, and for a few times I almost gave up, but Roger never gave up on me. With his great patience and goodwill, I am finally here, starting to appreciate the beauty of simplicity in geodynamic modeling, all because of his hours and hours and hours of mentorship. In addition, I also hope to thank my master advisor, Ansel, who introduced me to this fascinating field of geodynamic modeling and has been very supportive and encouraging since 2013. I also hope to thank my families and many other mentors and friends here at Columbia. Their encouragement, support, and love are essential for me to get to this stage. With this, thank you very much.
Thank you. We have some time, a little time. Let's take some questions from the audience, not from the committee. You get your chance later. So we got hands up or throw things in the chat. Is that a clap or a hands up, Jackie? Are there any questions?
Yeah, I got one.
Hey, Ben.
Hey, wow. Should we let a student go first, or is that just seminars?
Everybody jump in. I'd like you.
Okay. All right.
Go ahead.
This was, Kelvin, this was really, really beautiful work.
Thanks.
Thank you. And it was a great way to wake up this morning. I have two, but I'll only ask one unless there's time, and I'll send you an email with the other one. But the first one was on chapter 2. You had on the solid model that you showed for the high plateau.
Yes.
The numerical model, not the analytic one. For the thick black line, yeah, you have this extra uplift at the front, right?
Yes.
That, like the Colorado Plateau looks like that. But in the Colorado Plateau, the explanation for, one explanation, partial, is that there's elastic flexure due to thermal expansion,
right,
of the lower crust. And I was wondering is there a temperature dependent density in your model? And if so, could part of that uplift be that elastic flexure that's kind of liberal, where the crust gets very weak to the right? Or if there's no thermal, or is all of it, if there's no temperature dependent density,
right,
is all of that uplift just due to lower crust flow?
Yeah,
pushing up.
Yeah, we in our model we didn't consider the density is influenced by the temperature, because that probably compared to the mass conservation, because we basically intrude a lot of material into the lower crust. It will be a smaller portion.
A smaller effect,
yes. So we only consider the mass conservation and the lower crustal flow for relax that extra input of the crustal intrusion
Yeah.
for the surface
Okay.
evolution. Yeah.
Okay,
Oh, that's
thank you.
interesting. Okay.
Richard Seeger has a question in the chat. Can you see the chat, Xiaochuan? I can read it, but, or Richard, you want to ask the question?
I saw that chat.
So it says, given the uncertainties in carbon models and your own calculations of carbon flux, what should we make of the amazing agreement between modeled and reconstructed temperature change over time before the eruptions? To what extent are such results sensitive to model parameters, both in the geodynamic model and the carbon model?
Yeah, that's a great question. So there are several parameters that the model results are sensitive to. From the geodynamic model, the most sensitive are the cooling. Basically, as you can see, let me try to find that. So as you can see, from this figure, the depth of intrusion is very important to determine when the overburden density of the seal could be larger than that fluid magma. And the depth of the seal is a lot controlled by the thermal structure, as well as how fast it can cool down. So from this simple analytic solution, it can give us some insight. Basically, the shallow the seal depth, which means a thinner the heat can release to the surface, that will cause a higher thermal gradient. But if we have a Newton number, which are, for example, the hydrothermal cooling, that will enhance that heat loss to the surface. For example, at Yellowstone, it can be up to 20 times larger or faster heat loss to the surface due to that effect. Then the heat loss from the system will be much faster, and the seal depth will go back down much deeper, much quicker. So then the lag of the eruption phase to that of the warming phase will be a lot shorter. And also the other thing that's sensitive is the density structure. So the density structure control the length scale the seal has to go deeper, indicated by, for example, this one. If there is a initial very low dense crust, then the seal has to intrude very shallow and then go back down a lot deeper to replace the initial low density crust to be much denser in order to erupt. And that is a much longer process if replaced. So for example, take oceanic plateau as an example. The oceanic crust has on average higher density than that of the continental crust. And the intrusion is able to erupt much quicker than that for a continental crust. So our model didn't really consider the oceanic plateau cases. For the Losgar climate model, I'm not very familiar with all the parameters, but I know the climate sensitivity say the doubling of the CO2 concentration correspond to 3 degrees Celsius of warming. That could be very important. And there's also some other assumption like the area of the flood basalt, because the flood basalt, the basaltic composition will tend to cause the drawback down of CO2 due to the weathering much faster. And all that plays in how fast the cooling down could be. That's why we have actually very different coolback situation for Deccan Trap. As you can see, before the Deccan KPG boundary, the global warming is able to cool back almost back to the initial temperature. However, for the Columbia River, the onset of main phase flood basalt correspond almost to the highest temperature. So that could be due to the climate modeling part, where the environment setup is very different.
Thank you. We got time for maybe one or two, but Ben had a good point. Are there any students who have some questions? You should, here's your opportunity to jump in. Otherwise, Mike has one more question. Mike Steckler has one more question. Any students?
Yeah, great job. So in the same,
I guess Mike. Let me know.
No, I'm not muted. Yeah, so in the second model with the high and low plateaus,
Yes.
from the flow that you're getting out from the in the low plateau case, does that produce an elevated rim around the low plateau?
And yes. So as you can see probably from this topography evolution figure, initially it's flat, and because of the mass our conservation, the intrusion actually is able to uplift the surface at the beginning, but because of the denser intrusion that pull down the surface, actually the mass is redistributed to the surrounding and causing an uplifted rim, just like you said.
Okay.
Yeah.
All right. I think thank you all. Thank you all for coming. I think I'm going to ask everybody but the committee to step out of the room, as it were. Thank you all for coming. And I thought that's a great job, Xiaochuan.
Thank you.
All right, committee members, you want to take like just a couple minutes and get themselves up, grab some coffee, and let's get back in here and talk science. All right, I got to run quickly. I'll be back.